Okay, this is the video for the first part of lesson 4, integration by parts. We're going to skip the warm-up in the video. We'll do that next week. Moving on to the next page. The rule that we're going to see today is somewhat the opposite of product rule for derivatives. So, in fact, we're going to start with a version of the product rule for derivatives. I've got uv prime equaling u times v prime plus u prime v. And in the next line of work, I'm just changing the notation. I don't really love the primes. So here's another way to write these ideas. Derivative of uv with respect to x equals u times dv dx plus v times du dx. Having done that, I'm going to manipulate this formula a bit. Okay, in fact, I want to get the u times dv dx by itself, and that's what I've done in this third line of work here. Okay, once I'm at this spot, we're going to integrate both sides of this equation with respect to x. Okay, so every single term that was there is now sandwiched between an integral symbol and an extra dx, which is, of course, our integral notation. Having written all of that out, we can do some cancellations. So the dx that comes along as part of our integral work here can cancel out with these dx's and denominators all throughout. So I arrive at a statement here that says now integral of u dv equals 1 times duv minus v du. And I'm going to look now at this middle term, integral of 1. As we all know, the integral of 1 just becomes a variable. If it was integral of 1 dx, my result is x. Integral of 1 dy becomes a y. Integral of 1 duv becomes uv, whatever that is. So one of these three integrals, I can actually process it here. I'm going to leave the others as is, and apparently we've stumbled upon an idea here that's going to be useful. At a glance, it doesn't really become immediately obvious why it's helpful, but the integral of u dv can be rewritten as a u times v minus integral of v du. And the way we use this thing, if we can look at an integral in front of us and assign part of it to be a u, part of it to be a dv, we can possibly then rewrite the whole thing into something that's simpler. This is not the most common integral strategy that's used in this course. You should really never even attempt this strategy unless you've already double-checked that you don't have a top 20 and u sub doesn't seem to work. So this would be plan C in a way. Another clue is it's often used when you happen to be integrating a product of two functions, which makes sense because it's built off of product rule. So let's do the example 1 here. We need to integrate x times e to the x dx. It's not a top 20. U sub doesn't seem super helpful. Okay, if I say u equals x, for example, I still have really the same form of integral I started with. It's not clear how to work with it. I do happen to have a product here, so that's a clue to try integration by parts. So looking at my original integrand, I need to decide what part of this is going to be my u, what part is the dv. For this example, I'm going to say that this x right here, I'm going to call it u, which means everything else, the e to the x, also the dx, I'd have to call all of that dv. So dv equals e to the x dx. Now that I've got those parts assigned, I'm going to find a couple additional things. For example, this part looks similar to u sub. If I have u equals x, I could say du dx equals 1, or du equals dx, rather. With the dv, I'm going to work backwards of the work we would typically do with the u sub. I'm going to imagine integrating this informally. So I can say v is equal to the antiderivative of whatever value I'm seeing here. If I were to integrate e to the x dx, I get e to the x. Now, as I do that, I'm not putting a plus c. We never do plus c ever until the very end of a problem attached onto the final answer. So I'm just going to say e to the x. And now I have a u, a v, a du, a dv. I have got all the pieces I need to work with our formula for integration by parts. What used to be u dv, I can now package together as uv, so x times e to the x, minus integral of v du, e to the x dx. And as we step back and look at this, we realize this new integral is a lot simpler than what we had before. Integral of e to the x is just e to the x. The uv is still part of your answer, so I need to bring that along as well. X, e to the x, minus e to the x. Now I put on the plus c. So that's our first look at integration by parts. I would imagine the biggest question on your mind right now is, okay, well, how did we know what part of this was the u, what part is the dv? Because certainly your choices there matters. So seeing what we did with the u and the dv, we realize whatever I choose for u needs to be easy to differentiate. That's what I'm going to do with it. Whatever I'm choosing for dv has to be easy to anti-differentiate. Beyond that, I'm also going to give you, actually the most helpful thing is this little memory device, Lipit, Lipet, which is actually helping you remember a hierarchy of helpful choices for you. It starts with L, L standing for log, meaning if you have a log as one of the components of your product, that's usually always the best choice for you. And that could be base 10, it could be natural log, it could be any base of log. I stands for inverse trig. If you have an inverse trig component, that should be your U. Okay, if you have neither a log or an inverse trig, the next choice would be a polynomial P. If you have none of those three things, the next best choice is an exponential like e to the x or a to the x, 5 to the x, anything to the x power would be exponential. And then last in the order is conventional trig. I'm not talking about inverse. I'm talking about regular sine, cosine, tangent, those things. Okay. I've never seen a problem in Calc BC where Lipit didn't work out, where it didn't lead you to the right choice for that particular problem. So that's kind of like our go-to strategy for picking U. And whatever's not the U is part of the DV. We're going to see a few more examples here on the next page. Example 2, here we see a product, theta times sine 3 theta d theta. The product being, theta is technically a polynomial, right? It's like theta to the first, kind of like an x to the first. The other portion is trig. So with those two options, I would pull the theta as my u, which means sine 3 theta d theta all becomes dv. Differentiate the u becomes just du equals d theta. Anti-differentiate sine of 3 theta, there's a little mini u sub happening in here, right? We know the antiderivative of sine is negative cosine, but because there's a 3 multiplier, we need to see a 1/3 in that antiderivative. And now we have all the pieces we need. We follow the formula, which of course you should memorize. U times v is right here. Minus integral v du. I'm noticing the v also has a negative, so there is going to be a minus minus, which is why I write a plus. But then there's the 1/3, the cosine 3 theta, the d theta from the du. uv comes down as part of your answer. Integral of cosine is another mini u sub where you don't necessarily need to show the work, but make sure you put another 1/3 multiplier in there, which is why we end up with 1/9. But yeah, there's your answer. Don't forget plus c. Example 3 If this were to show up on a test, you wouldn't need to show any work. It is a top 20, would be the quickest, would be the preferred way to do it. But because we now know integration by parts, I'm able to confirm that this rule is what we said it was. In fact, natural log being a log, that's going to be our choice for u, which means the dv is just dx. Okay, here's my du, derivative of log. The dv equals dx, really it's 1 dx right here. So anti-differentiate brings you back to x. And now we go with the u times v, and all of a sudden it makes sense why there's an x log x in our top 20 there. Minus integral of v du. If you put the v and the du together, the x times 1 over x is just a 1. So you're integrating 1 dx, which is why you have a minus x as a second term. Don't forget plus c. So there's your proof. Top 20 is legit. Example 4 is not top 20. We have integrals related to arctangent, but the arctangent shows up in the solution. It's not the integrand. We've never actually seen this before, but that's okay. We know how to deal with it. Arctangent, inverse tangent lines up with the I in Lipit, so it's a really good choice for you. We know its derivative is going to be 1 over x squared plus 1 dx. The dv, meanwhile, was just dx. So again, we've got v equals x. Start putting the parts together. U times v minus integral of v du. Okay. This is not quite a top 20. The x on top makes it quite a different thing. So here I would do more of a conventional u sub. So yeah, it's possible that we do integration by parts in conjunction with u sub. Although I got to be careful, I really shouldn't use a letter u since we've already used that for something else in this same problem. So I went to w equals x squared plus 1. dw would be a 2x dx. I work that through all the way. I get my substitution going in the next line of work and eventually undo that substitution as well. Got just a couple more examples. Part of what I'm doing in the last two is also reminding you of differential equations with slightly different presentation of our work. And then in example 6, a definite integral. We can still see integration by parts with definite integrals. Okay, but we'll get to that in a moment. Example 5, differential equation given. We have an initial condition that we'll be able to use eventually. First step that you have to show is the separation. I've got my dy equaling x to the third log x dx, which means y is an integral of the right side. And now we look at that right side, we see the product, we see that it's not top 20. U sub doesn't seem like it's a good fit. We have a really nice choice for u if we do integration by parts, right? You got the natural log is the u. So x to the third dx becomes the dv. Differentiate one of those, anti-differentiate the other. Over here, I'm putting the pieces together, keeping in mind I need y equals as part of my answer if we started as a differential equation. So I'm going to keep that there for every line of work. I'm not going to be lazy or sloppy with that. Okay. I do have a much nicer integrand. I eventually get to my answer with the y equals and a plus c, but I can figure out the value of c by taking my answer thus far, plugging in 1/2 for y, 1 for x, solving for c, and then finally I update my answer with the plus 9 over 16, keeping that y equals in there as well. Last example for today, we'll do the rest of it next week. The definite integral, okay? I'm not going to worry about the bounds too much right away. My primary goal is to assign my parts, my u and my dv, going off of Lipit again. P comes before E, right? So polynomial x, u equals x is the choice. e to the 2x dx all becomes part of that dv, which when I anti-differentiate to get a v, I got to remember a 1/2 popping up there from a little mini u sub that's happening. When I put my parts together, u times v minus integral of v du, I do need to show bounds on this new integral. They wouldn't have changed at all. Okay. I go through and anti-differentiate. Another copy of 1/2 pops in, which is why I have a 1/4. At this point, be careful. The u times v gets carried down. It is considered part of your response, part of your answer. So now that it's time to plug in bounds to this antiderivative, I have to be plugging them into all of it, even the uv. So I've got these two terms here. I'm plugging a 1 in for x in both spots, which is where I get a 1/2 e squared minus 1/4 e squared. And then a minus sign from fundamental theorem. And then after that, I'm plugging a 0 into both of these things, which looks like I maybe skipped a step here, but it does turn into negative 1/4. Now I have a minus 1/4, which of course becomes a plus. My final answer is a number. I've combined some like terms. Keep in mind E is a number. Okay. We're going to call it right there with the video. If you have any questions, you can email me or come in the morning next week.